Hi, welcome to the video on the components down a slope. This is a thing that a lot of students have a bit of trouble with, so I'm going to do a video breaking down the ideas of what happens when you have something resting on a slope, and I will be talking about the angles on the slope and the reason why certain angles and certain components can be expressed in certain ways. This should be useful in mechanics as well as in physics. So let's get on with it. So here I have a block that I put it in faint dashed color because it's not so important, the shape of the block, and I've drawn in the center of mass of the object, and that's where the weight really has an effect. So I've drawn the weight down vertically because that's the direction it always acts towards the center of the earth. So this is a slope, and if this is horizontal and parallel to the ground, then that's the direction that the weight's gonna go, perpendicular to the horizontal and straight down at some angle to the slope. Now let's call this angle theta. They always give us this angle normally in questions, or sometimes they ask us to calculate it, and in that case they need to give us some more information. That's not a theta, that's an alpha. So theta. Okay. In order to know what is going to happen with this block, we always need to split the force, the real force that is acting, which is this weight, into components, as we've done in many cases before. In the case of the slope, the two components that interest us are one of them down the slope, parallel to the slope, and this will be responsible for any of the motion to do with this block in terms of that direction, directly anyway. And then the other component, we always split it in 90 degrees at right angles to the first component. So at 90 degrees to this one here would be, if this is parallel to the slope like that, then 90 degrees to that would be like that, right, straight up, perpendicular to the slope, like that, right? So this would be perpendicular here. So those would be the two components that we're interested in. One of them goes that way and the other one goes that way, and this is 90 degrees, right? So the weight, the real force, which is this one here, we're splitting it up in those two, and we can make a triangle with those two. So essentially, if we draw a representative diagram over here, then if this is the weight, then since that is the real force in this question, the biggest force in this example, then if we're gonna draw a triangle of forces, one of them going in that direction and the other at 90 degrees to that, then we need to make sure that this one, that's a terrible straight line. Let me start again. Okay, it's a bit better. And so if this is one of our components, then this has to be at 90 degrees to that component, and this is my real weight going that way. This is a component of the weight that is pressing against the floor, and that's going to be very useful in terms of calculating the friction acting on the block, because the harder you push against the floor like this in a perpendicular direction, the bigger the effect of the friction will be. So the other component would be, so this one would be that one here, right? And then this one here would be the one that's parallel to the slope. Okay, and even though I'm drawing the diagram, the line down here, and this is the triangle, when you're talking about forces, we've talked about this before, hopefully you can remember, it doesn't matter if I take this part of the triangle, or if I make another triangle here where this line is parallel to that one and this line is parallel to that one. This is then a rectangle, and since we care about the geometry of these forces and the sizes of the lines, then this line here, which will be W slope, i.e. how much of this weight is going down the slope, just there, is the same thing as this one here. The size of this and the size of this is the same geometrically, right? If we're using this angle here, let's call that angle alpha, we're going to be using this angle here mainly to calculate the different sizes of the components using trigonometry. And so if we use this whole W and that angle to calculate the size of this guy, then that's going to be the same as the size of that guy in the rectangle, right? So hopefully you can see that. And here we have W perpendicular to slope, then this is the same, perpendicular. Okay, so when you look at the block and you say, actually, well, I want this component, I'm not interested in this one, why would I be interested in this one? They are the same, the two sides of the same rectangle. Okay, so if I calculate this guy, then I know how much is wanting to go in that direction. That's the same thing. Now let's try to find out what relationship there is between this angle here, the alpha, and the theta that's here. Okay, let's see if there is a simple relationship between those two, because it would be really handy if there was. So for that purpose, I need to do a little bit of a zoom into the triangle. Okay, so I'll repeat what we're trying to do. We're trying to find the relationship between this angle, which is the one that we're going to be using together with the W in order to get this component and that component. And we need to find the relationship between that angle and the one that they normally give us, which is the one here of the slope. So let's continue this triangle and, well, let's draw it here separately. That would be better. If this is the line of my W and this is the one that goes along the slope, and this one is the horizontal, this is the perpendicular to the slope, so that's a perpendicular here, and we're interested in this angle here and comparing it with this one there. This is theta, that's alpha. Okay, and here I haven't drawn this one here, this perpendicular. I haven't drawn it because it won't help us so much in what we're trying to do here. So here we have two triangles and we can really have a better intuition without this line. But normally when we split this up in two components, we're very much interested in this guy and in that guy. They're the two ones that we're normally interested. This one would go down the slope and this one would go into the slope. Okay, so if we're looking at these angles, we said that if this is the line that's perpendicular to the slope, then this one was the perpendicular to that line, right? So sorry, this is parallel to the slope, then this one here would be the perpendicular to that one. That's how we drew our triangle, so that would be a right angle. And the angle we were interested in was the one that this perpendicular to the slope was making with the vertical one, which is this angle here. So if we want to compare these two, let's see if we can find out what this guy here is, because then we can find the relationship between them. So let's see, if this is a right angle up here and we're looking at this triangle, at the big one, then the angles in a triangle always add up to 180 degrees, right? So that angle here, which is 90, plus this angle here, which is theta, plus this angle here, which we're going to call x, that's got to be equal to 180, right? And so just for the record, we're looking at, not for the record, but just as a reminder, we're looking at that triangle, right? At the big one first, and then we'll look at this one, the little one, and this one later. So 90 plus theta plus x is equal to 180. So then what is x? X is going to equal 180 minus 90, which is the same thing as 90. Then the theta goes to the other side also, minus theta. So now we have a relationship between this guy here, which is x, and this guy theta. Okay, so x will be 90 minus theta. Now let's look at the second triangle, which is this one here, and try to find the relationship between alpha and the x, and therefore we can find the relationship between alpha and theta, which is in the end what we're really looking for. So again, this is 90 degrees because that's the weight which is going straight down, and that's a horizontal. So if that's 90 degrees, then alpha plus x plus 90 will be 180, right? So alpha plus x plus 90 will be 180. And so x will be, sorry, and then we need to express alpha. So we're trying to find, so alpha will be 180 minus 90 again, so that's 90 minus x. Right, so we nearly have it. Now we have alpha in terms of x, and we have x in terms of theta. But we want alpha in terms of theta. We want to compare this guy and that guy. So let's see if we can put these two equations together. Alpha equals 90 minus x, and we know that x equals that. So in other words, substituting this guy, we're going to put this guy into here, that x into there. Then alpha is equal to 90 minus x, and x is 90 minus theta minus theta, right? And this is a minus, so x I've got to include it in brackets to make sure that I don't make mistakes, because the whole of x is 90 minus theta. So this is 90 minus brackets 90 minus theta. So 90 minus 1 times 90, that's 0, and minus theta is plus theta. So conveniently, and this you can remember always, it's very useful, alpha and theta are the same angle. They're the same angle. So whenever you have a slope like that, and that is theta, then you know that if this is the vertical and that's the perpendicular here, then that angle there is always going to be also theta. Okay, so another way of thinking about it is if you think about rotating this guy, you've got this, and you think about rotating it like that, 90 degrees, right angles, then at the end of it, then you will get this guy here. Same shape. You've got this guy now is vertical, so this line here would be this one, and this line here at an angle, if that's theta, that line there would be the same as this line here. So if this is 1, this is 1. If this is line number 2, that would be line number 2. So if you rotate the whole thing 90 degrees, then you keep the angle. So hopefully you can see the relationship between those two angles in an intuitive way. And if you don't, and you don't believe me, then here was the proof of why they are the same. Okay, so I don't have very much time left. So I will go into the components and why the components are expressed in a certain way in the next video. But I'll just do a little revision here what we've done now as a recap. So when we're looking at the components down the slope, if there are no more forces acting, i.e. this is in the case where there is, you know, if there is a force here, then holding this up or whatever, then the components are affected by it, and you've got to take this force into account, and you can then split it up into, you know, if this is really the direction of the force, then there will be some component going down this way and some component going down up the slope. So the same as before, we take into account what goes perpendicular and what goes up, if there is an extra force here. But in many questions we don't have an extra force there, so we don't have to like add them or subtract them to the weight which is going to the components of the weight. And when we just have the weight and we're looking at this and say there is also friction, and perhaps in a question they tell us the friction is holding this and it's on the point of slipping, but it's not, and it's just being held there, then we know that if it's on the point of slipping, then the component of weight going down the slope would be exactly equal to the friction, right? But if it's not on the point of slipping, then if it's just being held there, then we know that the friction will be bigger than the force going down, and that's why it's staying there. The friction won't move the block up, right? It's just going to stop it from going down. So hopefully that makes sense. And so what we've talked about here is that if this is the weight, the component going straight down, then this guy here will be the component into the slope, and that we can calculate that using this angle, and we'll do that in the next example. And this will be the component going in that direction, which is the same as this guy here. Okay, so I'll see you in the next video.